In the next section in this chapter, we would like to kind of go back to what we did in the first section where we did displacement and distance traveled in a straight line, and now do that when an object isn't moving in a straight line. Maybe it's moving in the plane along some strange curve, or moving in space along some curve. The integrals that you get turn out to be much worse for distance traveled in space and in the plane. It's actually hard to give examples that you can do in a short amount of time. But the theory looks almost exactly the same if you give yourself vector notation and vector derivatives and notions of vectors. So what we're going to do now, this is the contents of Appendix A, an introduction to vectors and motion. This is here almost solely so that you can handle displacement and distance traveled in space and in the plane. This is not everything that one needs to know about vectors in like a physics course, but it should be a quick introduction and give you enough to handle many, many problems. Right. And you may have seen this in a physics course. That would make things much easier if you had already seen this in a physics course or a math course, but we're going to give you the essentials that you need for handling the problems in this book. So what is a vector physically? Physically, a vector is a quantity having magnitude and direction. So typical examples of a vector would be move 3 miles due north, or go west at 5 miles an hour, or a force of 10 pounds is pushing due south. You give a magnitude and you give a direction. What you don't give is a starting point and an ending point. So what does this mean? It means that I'm going to discuss this first in the plane, then hopefully the analogs for vectors in space will be clear, but I will state some of the things again in space. So here we are in the xy plane. A vector, something with magnitude and direction, but where the starting point and the ending point aren't predefined, like move 3 miles due north. Right? It doesn't say where you start, it doesn't say where you end up. Of course, if you knew where you started, you'd know where you ended up. So the way we represent vectors is by arrows that have the direction that we want and whose length is the magnitude that we're talking about, even if the quantities that we're talking about don't have length units. We represent them by arrows whose length is the magnitude. So for instance, 5 miles per hour due south, you'd still represent that by a vector with length 5, even though miles per hour is not in length units. So vectors are represented by arrows, but where two arrows represent the same vector, if they're parallel and point in the same direction, so their tails and heads are at the same ends, and they have the same length. So we represent vectors by these arrows. So I mean for all of these arrows to represent the same vector. Part of what this means is that, so if you start with a vector that starts at AB and goes to a point CD, so you have an arrow. It represents a vector, and the arrow starts at AB and goes to CD. We can write our arrow notation, A, B, C, D, our notation for arrows. So this arrow from AB to CD, well, we could, since it doesn't matter where the vector starts and where it ends up, we could always take our starting point to be the origin. So that means you drag this point down to the origin. It means you subtract A from the x-coordinate, you subtract B from the y-coordinate. And that's what you would do to the x and y coordinates up here. So this same vector or an arrow representing the same vector. If we drag the arrow to where it starts at the origin, you would get an arrow that goes from the origin to, you subtract A from here and B from here. That's what you do here and here. You subtract A and you subtract B. So that this arrow represents the same vector as the vector from 0, 0 to C minus A, D minus B. So what's the big deal? Well, the big deal is that means we can specify vectors just by specifying a point at the ending point of the vector if we assume the initial point is 0. So that it means that when we write the vector, we might write the vector um, 2 minus 5. Well, why isn't it the point 2 minus 5? Well, because we said it was the vector. It's just a different way of thinking of it. If you're thinking of it as a point, it's x is 2, y is minus 5. So yes, you might, if you just wrote 2 minus 5, you might mean the point 2 minus 5. But if you're thinking of it as the vector 2 minus 5, then that means you're picturing, or you're thinking of the vector represented by the arrow that goes from the origin out to 2 minus 5, and you would typically picture it by an arrow. So we just, we call it a vector, and that means we're thinking of it in this way. These are called the components of the vector. This is the x component of the vector. This is the y component of the vector. The magnitude of the vector. So we said a vector is something with magnitude and direction. What's the magnitude of the vector? Well, I said that we represent vectors by arrows whose length is equal to the magnitude of the quantity you're talking about. So it's the length of this arrow. That's the magnitude of the vector. And you should probably know, so it's the Euclidean length. Use the Pythagorean theorem. It's, you take this length squared plus this length squared and take the square root. So you just get the magnitude of 2 minus 5. This is the magnitude of 2 minus 5. It is, by definition, the square root of 2 squared plus negative 5 squared. So 25 plus 4, the square root of 29. In general, the magnitude of a vector in 2 dimensions, you take the square root of the sum of the squares of the components. So the magnitude of the vector AB. And when you take magnitude, magnitude isn't something you would do to a point. So when you're taking magnitude of something that you could think of as a point or a vector, you're thinking of it as a vector. And so you don't need to be told explicitly, AB is a vector, not a point. You're taking the magnitude of it. You're using it to represent a vector. This, by definition, is the square root of a squared plus b squared. There's only one vector that has 0 magnitude. And that would mean that a and b are both 0. So the magnitude of AB is 0 if and only if AB is 0, 0. And we call this the 0 vector. Just write a 0 with a vector symbol over it, a little arrow. A vector of length 1, of magnitude 1. If I ever say length of a vector, I mean the magnitude. It's actually a bad habit to get into because you don't want to think that all magnitudes are lengths, even though that's how we picture them. I try not to make that mistake, but every now and then. A vector of magnitude 1 is called a unit vector. There's a lot of terminology to learn. None of it's particularly difficult. Unit vector just means a vector of magnitude 1. So, for instance, the most obvious unit vectors, 1, 0, would be a unit vector. But so would, I don't know why I keep writing that. So would 1 over the square root of 2, 1 over the square root of 2. Because this would be the square root of this squared plus this squared, square root of a half plus a half. So 1. We define, I'm putting off the discussion of what direction of a vector means. In the xy plane, we kind of think of it as north, south, east, west, and then there's northwest, northeast. There are about 8 directions that have names, or you could go with north, northeast. So there are more directions, but there are an infinite number of directions, and they don't all have names. And I do want to say what direction means, even though it's a little unsatisfying. But I'm putting that off until I've defined 2 other things. So, with vectors, you have 2 operations that you can perform on. Actually, there are more, but 2 very fundamental ones that you can perform on vectors. There is vector addition. And it's defined in the easiest possible way, the way that you would define it yourself if you had to define it. If you have the vector AB and you want to add the vector CD, how do you add those vectors? You add the initial x coordinates. So you add A and C. So people say you define it component-wise. And you add B and D. So you just add the corresponding entries in the 2 vectors. So yes, that's the definition of vector addition. Again, you might think, oh, are these points or are they vectors? You're adding them. You don't add points. So when we write that we're adding 2 things that look like they ordered pairs of real numbers, so that, oh, you could be thinking of them as points. No, you couldn't, because you're adding them. That means you're thinking of them as vectors. That's vector addition. Vector scalar multiplication where you do not multiply 2 vectors in this. In a minute, we're going to have something called the dot product. But this scalar multiplication, the reason you say scalar is so that you kind of make it clear you're not taking one vector times another vector. You're taking a real number times a vector. In this context, when you're multiplying a real number times a vector, this is a real number. In this context, though, where you're multiplying it times a vector, this is frequently referred to as a scalar. And it's called that because it scales the vector. So by definition, scalar multiplication, R times AB, means you multiply each component of the vector by R. It does this. If you check, it's easy to see that the magnitude of R times AB is the absolute value of R times the magnitude of AB. So that what multiplying by R does, we'll see in a minute that it leaves vectors either pointing in the same direction or in the opposite direction. But what it does to the magnitude, if you multiply by r, the magnitude of your new vector is plus or minus, whichever one's positive, r times the magnitude of your old vector. So if you scalar multiply by 2, it multiplies the magnitude of the vector by 2. If you scalar multiply by minus 2, it multiplies the magnitude of the vector by positive 2. But the difference between multiplying by a positive scalar and a negative scalar is that multiplying by a negative scalar changes the direction. Of course, we don't have direction yet, so let me now say what direction is. It would help if I said one more thing here. Just because of how people usually write when I want to talk about, if you have 1 over r times a vector, so some vector v. So if r is a real number, not 0, so 1 over r is a scalar, a real number, you can multiply it times v, and this is frequently written as division. So when I write this in a minute, when I divide by a scalar, that's what I mean. I mean multiply by 1 over. Scalar, you probably would have assumed that if I hadn't said it. Oh, I guess while I'm defining that, I might as well define subtraction. There's no reason that you can't define vector subtraction. You just subtract component-wise. That is, of course, the same as, so this is subtraction. It's not usually defined as a separate thing because it's the same as taking AB plus, so you can use vector addition, the scalar minus 1 times CD. So those are the same. So it's no surprise. You can think of subtraction or you can think of adding -1 times the thing. And that's another piece of notation. -1 times a vector, we usually just write as negative AB, which is the same by definition of scalar multiplication. This is the same as you just negate both A and B. There are lots of things that you do when you're defining all these operations on vectors that you would guess even if nobody told you, probably. Okay, so what is the direction of a vector if the vector is pointing in some direction that doesn't have a name, like east, west, north, south? Well, this answer is a little unsatisfying, but let me try to justify it before I state it. So here's some vector v. Assume that's not a direction that has a name. What do you mean by the direction then? You know, that's pointing in some direction, doesn't have a name. Well, we just need to be able to say when two vectors have the same direction. Well, what we could do then, if we start them all at the origin, so by writing vectors as just pairs of real numbers, we are imagining them all starting at the origin. So having the same direction would just mean, well, they're on top of each other, but maybe it's smaller than this one, maybe it's bigger than this one, maybe it's exactly this one. How do you tell? And the answer is, well, we make them both the same length and then see if they're the same. And then they have the same direction. What do you mean? Well, so what length do we make them? Well, not 0. What we could do is say two vectors have the same direction if they're the same after we make their lengths 17. But after 0, the only other kind of a really nice number is 1. Okay, that's not completely true, but 1 is easy to deal with. And so what we do is we make the vector a unit vector. Now, I don't mean you leave the vector the same, but you define the unit vector in the direction of v. So suppose v is not the 0 vector. The unit vector in the direction of v. is you take v and you want to make it a unit vector by multiplying by a positive scalar. So we multiply by 1 over the magnitude of v, and this is normally written as v over the magnitude of v. This certainly has magnitude 1, because if you take the magnitude of this, you pull out the scalar, the absolute value of it, but this is already positive. By the way, v is not the 0 vector, so the magnitude of v is not 0, so 1 over it makes sense. And the norm of the magnitude of this, you pull out this, so you'd have 1 over the magnitude of v times the magnitude of v, those would cancel. This is the unit vector in the direction of v. It is the only unit vector that has the same direction as v, and the nice way to define the direction of a vector is to say the direction of the vector is this unit vector. Now that's unsatisfying. So you're saying the direction of a vector is some other vector that has length 1 and points in the same direction. Yes, that's what we're saying. It's a little unsatisfying, but you have an intuitive notion of direction in some directions, and that's fine. But for all those directions that don't have names, what do? Well, this is the best we can do. This is technically, mathematically, what you call the direction of v. So two vectors have the same direction if and only if after you divide them by their magnitudes, or multiply by 1 over their magnitudes, you get the same vector. What about the 0 vector? We have to make a decision. Certainly this does not apply to the 0 vector, and yet we like to talk about directions of vectors, and we want to know, we'd like to be able to say sentences about directions and not have to say something specific about the unit vector, say as long as the vector is not 0. So there are two obvious choices. We could either say the 0 vector has no direction or that it has every direction. It is fairly standard, and we're going to adopt this convention. We'll say the 0 vector has every direction. This is convenient in a number of statements, and intuitively it sort of makes sense, because going 0, if I move 0 feet north, that's the same as moving 0 feet south, and it's the same as moving 0 feet west. It's the same as moving 0 feet in any direction. So yeah, the 0 vector, its magnitude is 0, but its direction, thinking of it as having every direction is fine, because going 0 in every single direction gives you the same thing. So anyway, when we talk about the direction of vectors, we will assume the 0 vector has every direction, because that'll simplify some of our statements. Okay. I do want to define a very useful operation, a product operation that you do to two vectors, but it's not as though you multiply two vectors and get a vector back. You multiply two vectors and get a number back. So this is called the dot product. We really won't use this much in this book, but it would be a shame not to talk about dot product while giving this introduction to vectors in motion. It comes up very often in other contexts. So the dot product, you take two vectors in R2, the dot product of two vectors, you multiply the corresponding entries like you might think for product. Oh yeah, if addition is you add A and C and you put a comma and you add B and D, multiplication should be you multiply A and C and you multiply B and D. Well, it turns out that component-wise multiplication really doesn't come up as an interest, as kind of a relevant operation to do to vectors very often. But the dot product does, and it's a number, not a vector, and it's what you get if you do multiply the corresponding components, but then you add them. So it's the number AC plus BD. It may be hard to believe that this is an interesting or a good operation. It has several nice properties. It's commutative, meaning that the dot product of two vectors, v dotted with w, is the same as w dotted with v. All of these are easy to verify. It's true that it distributes over, well, kind of scalar multiplication and addition. Okay, I shouldn't say that. It's a linear operation. Some people say bilinear. It distributes over addition, but you can also pull out scalars. So here's a scalar A, a scalar B, two vectors, and I take the dot product. This is the same as taking the scalar A. So you kind of distribute this dot product and then pull out the scalars. It's the same as taking the scalar A times the dot product of u and v plus the scalar B times the dot product of u and w. I say some people would refer to this as bilinear because if you combine it with commutativity, you could put the a plus bw over there and the u over here and distribute and pull out the scalars the other way. It's also true that v dotted with v is the magnitude of v squared. That's easy to see because if you take ab and dot with ab, you get a squared plus b squared. But that's the square of the square root of a squared plus b squared. So yes, that's the magnitude of the vector ab squared. So that's nice. But the dot product, one of the reasons or the main reason it's so important, is that it has a geometric interpretation that is distinctly non-obvious from its definition. Its definition just looks kind of almost silly. But you can show, using trigonometry, that, in fact, this is the big deal. The dot product of v and w is the magnitude of v times the magnitude of w times the cosine of the angle in between the vectors. So where theta equals the angle between v and w. This is important and cool. So, you've got some vector v, some vector w. There is some angle in between. The angle might not be acute. It might be obtuse. So this is why the dot product is important, because it has this geometric interpretation. So you use the definition to calculate the dot product if you're given the vectors by being given components. So if you're given two ordered pairs of real numbers and you calculate the dot product easily, but then it tells you this. So this is how you find the angles between vectors if you want. Right? If v and w are not zero, so v is not the zero vector and w is not the zero vector, then another way of writing this is that the cosine of theta is v dot w over the magnitude of v times the magnitude of w. And you could take inverse cosine, and that would give you the angle, theta. So you can use dot product and magnitudes to give you the angles between vectors that are given to you by specifying components. Another important thing about this is it says, when would the dot product be zero? Well, the dot product would be zero if one of these three quantities is zero. But if we assume that v and w are not the zero vector, which I wasn't assuming when I wrote this general formula. This formula is true if v and w are the zero vector. But just temporarily, assume v and w are not the zero vector. Neither one of them is a zero vector. Then v dot w would be zero if and only if the cosine of theta is zero. But that would mean that the angle between the vectors is pi over 2. So think 90 degrees, pi over 2 radians. it means the vectors are perpendicular. And so this line, I claim, tells us that v and w are perpendicular to each other if and only if the dot product is 0. What am I writing? Notice this is the number 0, the scalar 0. The dot product of two vectors is a number, not a vector. All right, I didn't write in this line that v and w aren't the 0 vector. This is one of those times where it's very convenient that we said the 0 vector has every direction. So if v and w are not, if neither v nor w is the 0 vector, this line tells us that v and w are perpendicular if and only if the dot product is 0. What if one of v or w is the 0 vector? Is it true then they're perpendicular, that if and only if the dot product is 0? Well, if one of v or w is 0, certainly this is true. But are the vectors perpendicular to each other? Yes, because we said that the 0 vector has every direction. So as soon as one of these vectors is the 0 vector, this is true, but this is also true because we said that the 0 vector has every direction. So in particular, it's perpendicular to every vector. Okay, those are basic operations with vectors in the plane. All that changes in space is that you have 3 numbers in order, so that you represent a vector in XYZ space, so in R3. So you just represent it by, well, an arrow starting at the origin and going out to the point ABC. So once again, we talk about a vector, and we use notation that could mean a point, but the context, either we say explicitly that we're thinking of it as a vector, we write the vector v equals ABC, or we perform some operation on it that makes it clear we're not thinking of the ordered triple ABC as a point, like we take its magnitude, or we add it to another point. So we add it to another ordered triple, so then we're thinking of them as vectors, or we scalar multiply it. So all of our notions that we had before generalize easily to 3 dimensions, right, and actually generalize to any number of dimensions, but we don't want to get crazy today. So the magnitude of the vector ABC is just the square root of the sum of the squares. So the length of the arrow that we would use to represent it from the origin to the point ABC. Adding to scalar vector addition is defined component-wise. You just add the corresponding components. Scalar multiplication is defined how you would expect. A scalar r, so a real number r times ABC. You just multiply each entry by each component by r. The dot product of 2 vectors, you multiply corresponding components and you add. And it's still true that the geometric interpretation of this holds. This is the same as the magnitude of ABC times the magnitude of DEF times the cosine of the angle in between. So where theta is the angle in between this vector and this vector. The dot product is still, just ignore that I've got a pair here. The dot product in 3 dimensions, still commutative. You still have this linearity property, and certainly the dot product of a vector with itself is the norm of the vector squared. So this is a quick, very quick introduction to vectors in the plane and in space. There are lots of other things to say. I haven't talked about standard bases for R2 and R3, and I haven't talked about what it looks like geometrically when you add vectors. But what I do still need to talk about is motion and vectors, how vectors work with motion. So let me do that. So we have vector functions, and then next time we will really start distance traveled in space and in the plane. So what's a vector function? Well, for us, we're going to have functions that take a real number and give us back a vector. So it'll look like, yeah, you can think of it as giving you back a point, but in fact, we're thinking of them as vectors. So we have some function, p of t, which I'm going to write this in 3 dimensions, and in 2 dimensions, just ignore the z component that I'm going to write, or set z equal to 0. We frequently think of the where z equals 0 in xyz space, where z is 0 is the xy plane. Well, it's the xy plane with a 0 sitting in the third coordinate component, but so it doesn't matter whether you ignore that third component, just pretend it's not there, or set it equal to 0 if you want to know what happens in the plane. We're going to have, so this will be our domain will be some subset of the real numbers. So a vector valued function. You give some real number t to the function, and it gives you back a vector, which looks like a point, of course, which means you get three functions. These are called the component functions of p. These, because think of this as your position, maybe the position of some object in space at time t. Well, to specify the position of some object in space at time t, what you do is you specify its x-coordinate at time t, its y-coordinate at time t, and its z-coordinate at time t. So these are called the component functions. And yes, if this is representing your position, this is just called different people would call this different things. It might be the position function, the position vector. But really, you just get used to thinking of things in terms of vector and in terms of vectors. And what most people would call this is just the position without saying anything else. The position is, you always think of it as a vector that starts from the origin and goes out to the point where your object is at time t. So, right. That's, we call this a vector valued function, but the notation makes it clear that that's what we're getting, a vector valued function. It's continuous. P of t is continuous. If and only if each of its component functions is continuous. It's differentiable if and only if all of its component functions are differentiable. P of t is differentiable if and only if x of t, y of t, and z of t are differentiable. And when this is the case, so when x of t, y of t, and z of t are differentiable, and in this case, the derivative of p of t, by definition, is, well, you write the limit that looks like derivative, or you could just say you take the vector that has the derivatives of the component functions. For components, those are the same. You can either take the limit as h approaches 0 of p of t plus h minus p of t. Right? These are vectors. These are vectors. We know what it means to subtract. This dividing by h really means multiplying by the scalar 1 over h. And that really, if you write this out, it just gives you this limit in each of the components, which means you just get the derivative of each of the components. So taking derivatives of vector value functions is about, well, it's just as easy as taking derivatives of the functions that you're used to, except you have to do it 2 or 3 times, depending on how many components you have. Okay, great. So what? Differentiation of vectors. Differentiation of vectors has the nice properties that you're used to, like of vector functions, that if you have a constant, so a scalar times this vector function plus a scalar times some other vector function, and take the derivative, you can pull out the scalars and split up the sums. So differentiation of vector valued functions is still linear, so it means you get this. It's a little surprising that there's a product rule for dot product. A little surprising, maybe not a lot surprising, but if you take the dot product of 2 vector valued functions and you take the derivative, then it looks like the product rule for functions of a single variable, but where product now means dot product. So you take the first function without a derivative, but you dot it with the second function, but it derived, so the derivative of the second function. And then you put the prime on the other function and dot that with q of t. That's easy to verify. You just check it, and that's what you get. And then we'll deal with integration in the actual section where we use this appendix. But it is worth stating explicitly that if p of t equals the position of an object, at time t, then its derivative, it's a vector valued function, but it's the instantaneous rate of change of the position function, the position vector. It's a vector in and of itself, and that vector is called the velocity vector. But most people just say velocity because you're used to thinking in terms of vectors. So the derivative of the position function with respect to time, this is the velocity vector. And the derivative of the velocity is the acceleration, but acceleration is now a vector. So it's the derivative of the velocity vector, or what's the same thing, the second derivative of the position vector. This is the acceleration. And then I'll say one more thing. Most references at this point By the way, I was assuming this was differentiable so that p prime exists and that the velocity was differentiable so that v prime exists. Most books, most references at this point, would call the magnitude of the velocity vector the speed. And we can do that. So the speed equals the magnitude of the velocity. This is kind of what, it's what you expect, that, yeah, velocity has a direction and speed is just the magnitude of that. So for instance, when we even had motion just in a line, velocity could be positive or negative, indicating which way you were going. But the speed was just the absolute value. Well, that is the magnitude of a real number. It's its absolute value. And so, yeah, this should make sense. Instead of saying, oh, if you say you're going 3 miles per hour northwest, the magnitude, so that's your velocity, your magnitude is just 3 miles per hour. It's a number, it's a scalar, the magnitude of the velocity vector. Having said that, earlier we kind of said that, oh yeah, but if you want to think of speed as an instantaneous rate of change of something, it's the instantaneous rate of change of distance traveled. And there's kind of some advantage to thinking of speed first. Its definition is the instantaneous rate of change of distance traveled, and then seeing that that's the same as the magnitude of the velocity. Okay, well now we're saying, oh, speed is the magnitude of the velocity, but we'd still like to see that this is the same as the instantaneous rate of change of the distance traveled by the object. But that's what we'll do in the section, not in the appendix, but what we'll do in the section on distance traveled in the plane and in space. So we'll stop this here and go back to chapter 3.